laser irradiated Dirac.
Okay, so thank you very much for the introduction. I'm Takashi from ISST at the University of Tokyo, and today I'll talk about this effect of applying circularly polarized laser light to three-dimensional Dirac semimetals. And yeah, you saw this animation. So today's morning, there was a lecture by Dr. Sales about this trying to transport water with a glass. So it's kind of, my talk is kind of the same line, but now let's imagine that I'm stirring this glass in a circular way and try to understand what will happen there. Okay. And it's okay, so this is, so using my 40 minutes or 30 minutes, I'll try to explain this certain phase diagram, something like a phase diagram that, with two axes. So this axis is the strength of E. So this, if I go one slide back, so E is the strength and omega will be the frequency. And so that's this two axes. So here I have photon energy, here I have E. So if I go up in this direction, my field is going to be stronger, or you can also say that my rotation becomes larger and larger. If I go this way to the right, my photon energy is larger, so I'm going to do this process faster and faster and faster. And okay, so you kind of know, okay, so this workshop, there's a large focus on Fourier physics, and a lot of the Fourier physics become very simple theoretically in the large omega limit. It's actually this region that Fourier theory works very well. Also for weak field, we have many already well understood processes like perturbative optical process, like second order process, CPGE, and so on. That's like this very weak field finite omega regime. Also, like if we have carriers in our system, the carriers will start to move, and there will be some rotation or movement of the carriers. But then if we go to the large E, but slow field or small omega, then we'll go to this tunneling regime. So in this regime, our field, so it's so slow that our particle or our quantum system do not remember that it's periodically driven. So it only reacts against the maximum value of the field. So in that limit, we have this tunneling problem. But still, okay, so during this talk, I want to explain that there will be like a zoo of geometric effects. So at each of these examples, there will be some geometric effects. Especially, especially, I'll try to focus on this Fourier limit. This is relatively already well understood. So we'll have this Fourier, okay, so for three-dimensional Dirac system, we have this Fourier wire points and emergent Fermi arcs. On the other hand side, if we go to the tunneling regime, okay, so in the simplest example, we have this Landau-Zener tunneling or non-adiabatic tunneling regime. But then we've actually found something very interesting, that there are some geometric modification to the Landau-Zener formula, which is known as the twisted Landau-Zener formula. Actually, Berry himself already studied this effect in 1990. So this is a paper, not the Berry phase paper, or not the famous counter-diabatic paper. He has another paper in 1990 talking about geometric effects in quantum tunneling process. And I'll try to show that there's some modification which is related to this geometric amplitude factor that he names, but yeah, it's related to the Berry connection. Okay, so that's the kind of the outline of my talk. And okay, so with this slide, I want to acknowledge my collaborators, especially for this tunneling part. I worked with Shintaro Takayoshi and Jianda Wu. And now we have this, about this Froke part, we have this theory and experiment big collaboration with the group of Shimano in University of Tokyo. Also, the organizer Aditi, she's one of my collaborator in this project. So about this crossover between the Froke and the tunneling regime, actually this is a very, very old subject already studied in 1965 by Keldysh himself. It is known as the Keldysh crossover. Keldysh was studying this very simple problem of having one quantum particle in a trap, and instead of having a DC field, he's considered applying an AC field, so oscillating electric field to this atom, and studied how this particle will escape from this potential. Okay, so in this problem, the very important quantities are the size of the gap, or you can say this size of the energy difference, and also, of course, the width of this wave function, Z. So that's like this, that's how far my quantum particle can penetrate through this barrier. And this becomes very important. And what Keldysh observed, actually he studied, found the exact solution to this problem and took two limits. One limit was this tunneling limit where this DC field, this omega, this frequency becomes smaller and smaller. Found out, as we expect, that this particle will tunnel through this barrier. You get this tunneling probability, which is exponential of delta over E, where E is the field, delta is the energy gap, and Z was this like the length of this quantum mechanical particle. So in this limit, it's this formula is actually very intuitive to understand. It's the ratio of delta against Xi times E. Actually, that's the number of arrows. Okay, so this arrow is the size of this wave packet, which is Z, and I have to penetrate, like in this example, 3 times the width of my particles. So this delta over Z over E will be 3 in this example, exponential minus 3. On the other limit, where I have like a multi-photon process, I will tunnel through, I will be excited by absorbing several photons. And of course, in this process, the excitation takes place in a power way. This power is given by this the number of photons I need to absorb. That would be delta divided by omega. And then the crossover between these two pictures are obtained by considering the ratios, okay, of this number of arrows. So I had 3 arrows in this way, maybe 4 arrows going up. The ratio of those number of arrows is given by this, in this case, omega over Ze. This is known as the Keldysh parameter. If the Keldysh parameter is small, you're in the tunneling regime. If it's large, you're in the multi-photon regime, which is more or less in the Froke picture. Okay. And then, okay, now I want to kind of extend this idea to our problem, which is a 3-dimensional Dirac electron in circularly polarized laser light in a very simple Hamiltonian. So just a 4x4 Hamiltonian where I have this wire component here, and sometimes I have this mass term M, but usually I don't even need this mass term to have the geometric effects that I will explain today. Okay. So again, to this phase diagram. So let's go step by step. Oh, actually this is again this picture, this movie. And you know that there will be some, if we have excitation, that's like spilling this water or wine, that's a quantum excitation in our system. And if you write these various processes, again, we have this Froke process, 1 over omega high frequency, 1 photon and multiple photon picture, and then the tunneling limit, and low omega, we have semi-classical and perturbative. And okay, so as for the semi-classical, as I mentioned, again, so if we have carriers in our material, the system, the carriers will try to follow the electric field, and that motion will generate some anomalous current, as we know. It's kind of like a quantum Hall effect. But then in the perturbative regime, if you apply circular polarized light to 3D Dirac or wire system, actually this was already studied by these people in a few years ago. And actually there was already an experiment in MIT about the photocurrent in three-dimensional wire system. So you get, okay, the point is that the optical selection rule. So if you have a wire electron and you consider photo excitation, the excitation probability is different. It really depends on the momentum position. It can be big here and small here. So you have more excitation here. And of course, this transition probability, transition dipole, is given by the Berry connection. So the Berry connection is strongly dependent on the momentum. So that's why you get this strange behavior. Actually, recently, many people have been studying or extending this idea of using the idea of geometry in order to study the laser-induced nonlinear photonic processes. So, because, as I said, this optical process have this transition dipole, and transition dipole is the Berry connection. Berry connection itself is not gauge invariant, but all physical quantities must be gauge invariant, and thus all physical quantities, if you do the calculation properly, they are written using some gauge invariant quantities, not just the Berry curvature, but even higher order quantities such as the Hermitian curvature. So in the paper by these guys, they found out that the laser-induced Hall effect will be given by this Hermitian curvature. Okay. So that was the kind of review of those low energy, low field limit. Now I will move on to the Froke picture. So, okay, so I won't go into detail about the Froke band theory so much. So it's really like a time-dependent, like a Fourier transformation in the time direction. So if I have a time-periodic Hamiltonian, so I can rewrite my Hamiltonian or rewrite my Schrödinger equation using the Fourier basis. And okay, so the picture is that I have, so let's say I have a three-dimensional Dirac system. Then I have a copy of that here. And then I have a replica copy, which is shifted in energy by capital omega upward. So H naught plus omega. And here H naught minus omega. This ladder actually goes up for infinity. So I have a ladder of Hilbert space in my effective system. And then these different replicas, they will couple to each other through the coupling given by the Fourier transform. So the non-zero Fourier transform of the time-dependent Hamiltonian, which turns out to be the current operator in this example. By diagonalizing this kind of Hamiltonian, we get the Froke eigenstate. So now, by diagonalizing this Froke problem, we get Froke bands. So this is in momentum and energy space, and we have very complicated band structure. But I'll try to explain this a little bit more easier. One key feature in this Froke bands, actually this is already quite a long time ago, but there has been some work on Froke topological states or Froke topological insulators that you can control the topological number of these Froke bands by considering appropriate excitation or appropriate periodic driving of the system. Actually, there has been like several examples. One example was like if I start from a Dirac system and consider this a small omega limit, small omega. Sorry, it's opposite. So large omega limit, and I focus on the low energy region, like around here, you can have effective Hamiltonian, which is in the high frequency effective Hamiltonian, and you can open a gap in a 2D Dirac system and turn it into a two-dimensional Chern insulator. Actually, in a very similar time, these people in the second paper, they propose a different type of realization. Actually, they consider the original band, so this red or pink and the blue one. They study the situation where this blue one has a copy, this photo-induced copy up here, and then there's a gap opening between this photon-absorbed replica band and the original band, and you get a gap opening. And even at this gap opening, you can get a non-trivial topological state. The point is that here, the gap opening is proportional to A naught. A naught is the electric field. It's actually the gauge field of the circular porous light. So it will be E over omega. So this one photon resonant gap opening and high frequency gap opening, there's kind of two directions to obtain this gap opening. Okay, so as for this example that I showed, this was just numerical plot of the two Dirac, three-dimensional Dirac system under circular porous light. You can see both examples. For example, for the small energy limit, we have two wire points. Originally, this was a three-dimensional Dirac point, but that Dirac point splits into two wire points. And we get a Froke wire semi-metal with a higher gauge field, giving this splitting of the wire points. Then, actually, if we focus or look up here in energy, we see another strange structure. If I just look into one hierarchy, so Dirac system is given by left and right wire components. If I look at one wire component, it's much easier. It's really, so this is the original Dirac point down here. And this is the upper band. There was a lower band or occupied band, but that occupied band will move up here as a one photon absorbed state. And that one photon absorbed state and the original upper band will be hybridized, and there's a gap opening here. But this gap will close at this point. Actually, if I go to the other wire component, I have a wire point here. So there will be wire point here and wire point here. Actually, this wire point, it's not the usual wire point, but it's a double wire point. So it has effective Hamiltonian like this. So then, actually, recently, there has been some experiment in Shimano group trying to measure the whole conductivity that is emergent because of this wire points. I won't go into the detail of the experiment. If I try, okay, so since I have wire points, let's imagine that I have like a slab geometry. So I terminate my material. This will be the upper surface, and this will be the lower surface. And if I have the circular porous light applied to this material with a certain angle, so not just in the z direction, but with some angle, then my wire point will split in parallel to this laser field, which will generate some Fermi arc edge state. So it's like an edge state, but it's actually a Fermi arc, which is parallel to the surface. In the upper surface, it will be in this direction. In the lower surface, it's in the opposite direction. If we look at the Froke spectrum, we see this Fermi arc near the low energy limit and near this one photon resonance limit region. And since near the low energy, I have one Fermi arc at each surface. And for this one photon resonant part, I have two Fermi arcs because my wire point was a double wire point. And we see, okay, so actually there's an experiment also in Shimano group measuring this current. that is generated in the material, we still don't know so precisely, but we think that these surface states that we have here are, so they would generate some current, and we think that this current that was experimentally observed are related to this surface state. So, yeah, okay, I don't know how much time I have, but enough time? Okay, thank you. Okay, thank you very much. So with the remaining time, I'll try to move to this second half. This part was the Floquet part, and this part, actually, the idea is very simple, and the message is also very simple. I'll just try to explain this single formula and how to use it or apply it in a wire system or Dirac system. Okay. So now let's consider, so not the Floquet limit. In the Floquet limit, our laser is periodically driving, but in the slow limit, my field is so slow, my electron will forget that he was periodically driven. So then, okay, so in this system, my momentum K will move within the Brillouin zone as K plus A. And for each K point, I'm going to move around like this. So if I just focus around here, so during this motion, the gap becomes smallest around here, where my K point approaches the Dirac point. Okay, so now this image is more like a gap to Dirac system. Okay, so I focus around here. I magnify it like here, and let's think this in the space of this three-dimensional space with Pauli matrix, sigma x, sigma y, and sigma z. Actually, okay, so this is related to the paper by Betty. So we know very well that if we have quantum dynamics starting from the adiabatic limit, so the slow field limit, are excited. So my solution to the Schrödinger equation, it will follow the adiabatic solution. Let's say it's 1. And if I don't have tunneling, I have some dynamical phase plus this additional geometric phase, which is known as the Betty phase. That's this very famous paper by Betty in 1984. But then if I start to make this field faster and faster, then I'll start to have some transition to the excited state. Let's say that's 2. So 1 to 2. Then I have the square root of P and square root of 1 minus P, where this P is the tunneling probability. And then Berry found out that even inside this P, the tunneling probability, there are some geometric effects. So there was a paper, so he wrote this paper, Geometric Amplitude Factor in Adiabatic Quantum Transitions. In 1990, he considered a very strange time protocol. So he considered a very complicated time evolution like this, going up. This space is the same space as this space of Pauli matrix. So I have, he had this three rotating part and this linearly increasing part in the Z. Actually, so the problem, okay, so this problem was a little bit complicated. We can even make it simpler to this Hamiltonian. I think this is the minimum model to study this geometric effect of Berry. So as you can know, so this Q is F times T. So it's the time parameter. So this is a good picture. So Q is our parameter. We have 2 bands, 1 and 2. We're interested in the tunneling from this band to the upper band. Usually, we know we use the Landau-Zener model. So that's this first 2 part in the Hamiltonian. M is the gap size. Q is our linear increase. And then let's think about adding this third term. So that's this second Pauli matrix and a quadratic term, Q square. So this looks very harmless, like it's Q squared. So like in perturbation, I would think that this doesn't do any effect. But then it turns out that you can, actually you can calculate the tunneling probability for this model. And it turns out that, okay, so there's a modification to the Landau-Zener formula. You can see actually this part, F times kappa over 2. This is the modification. If I didn't have it, it's the, sorry, what's maybe, okay, good. Hope it's good. So if I didn't have this, it's just the usual Landau-Zener formula. Now I have this F times kappa term. F is the speed and kappa is this term. And if you can, you can generalize this in the sense that this kappa, okay, if I consider the, using the language of Berry connection of these two bands, I can rewrite this expression like this. So M is upgraded to delta E and kappa is upgraded to R plus minus, where R plus minus is the diagonal part of the Berry connection between the two bands. And it's a phase difference of NM. In the language of crystals, this is known as the shift vector, which is gauge invariant. Good. Actually, this was the most, maybe this is also important. So let's look at this formula. So what do we see? One part is that I have F here. Here I have the absolute value of F. Now this is F itself. So the sign of F will matter. So whether I have positive or negative F, my tunneling is different. If I go back, if I tunnel from left to right or right to left, the tunneling amplitude is different. This is known as rectification or non-reciprocality. You can see this in this, okay, so this is a very busy plot. I'm sorry, maybe the red data is good. So this is F and maybe the black one first. Black one is the usual Landau-Zener. My tunneling amplitude is 0, but it increases if I make F larger or smaller, negatively large. But if I have this shift vector or this R, if I go to the right, it goes up and it goes down. If I go to the left, it goes up and it goes down. And the left, positive and negative F are different. We also find that this square, it becomes 0 at some point. We call that perfect tunneling. So it's a perfect tunneling. So the wave function will tunnel to the excited state perfectly. And then I'm not sure if this is the right word to use, but when the speed becomes faster, the tunneling probability becomes smaller. The faster you go, the less transition occurs. Okay. And then, the rest is applying this to 2D and 3-dimensional Dirac systems, which is kind of obvious. So we just consider excitation. Just for each momentum point, we calculate this tunneling probability and plot it against each momentum. And we find out that if we have circular porosidite in the Z direction, our excitation will be something like this. And you see that there will be more excitation in the plus Z compared to the minus Z. This means that there will be a current in the direction of the laser field. This is exactly similar to the photocurrent in a wire semimetal, but due to a tunneling mechanism. So it's not one photon absorption, but it's a tunneling mechanism. But the consequence is that we get a current. So this was the one photon absorption, and this is the tunneling. Kind of similar expressions, but our Berry connection is the optical transition dipole is replaced with this tunneling probability, which has this geometric effect. And again, we have very similar to here. Now our excitation is like this. It has a imbalance between positive and negative K. Also, some difference is that in one photon absorption, the energy is kind of conserved. So I only have excitation here and here with 1 omega difference. Here, my excitation is more continuous because energy is not conserved in a time-dependent perturbation. Okay. Yeah, and this is like how a crossover takes place when I make the field larger and larger. Yeah, you can find this. This is detailed, so you can find it in this paper. Sorry. Another maybe experimentally relevant situation is to apply this circular porous light to a two-dimensional Dirac system like TMD. So you have K and K prime points. You can have circular porous laser light. It is well known. 10 minutes more. Oh, thank you. So it is well known that Chan Yu and his collaborator theoretically predicted that it's not so difficult to understand that there is a very strong optical difference in the optical selection rule. So K and K prime, they have different chirality. You can excite more carriers in one chirality under a certain circular porous laser light. So I have more dots here than here, so more excitation here. And this is called photoluminescence effect. This photoluminescence and the difference, photoluminescence is basically given by the square of this very connection, which is different from left this K and K prime point. In the same way, you can consider this. Okay, so this is optobarytronics. You can do something like a tunneling barytronics with your laser field smaller than your gap. And then the result is kind of similar. So your K and K prime point, the excitation will be very different. And it looks something like this. Again, we have this geometric term around here, and this will strongly modify the excitation. The ratio between K and K prime point, so this gamma, will be it's just the ratio between this with positive and negative xi, which becomes a very universal expression. I have just an exponential of omega m over E. So it depends on the mass gap, but the rest is just omega and E. Okay, so this is my final slide. So with my talk, I try to explain this zoo of geometric effects that happen when I have a Dirac electron in circular porous limit and in laser field in various limit. So here we have Fouquet physics, and going to this slow limit, we have a geometric effect in the tunneling regime. Of course, in my theory, we don't have, not like Keldysh. Keldysh had an exact expression from here to here, but in my talk, it's really trying to understand this limit and this limit separately. Okay, but thank you very much. That's all.
Thank you, Takashi. Questions? Maybe I can start by asking one. Can you go back to the minimal model for this geometric Landau-Zinner transition? Yeah, right. So tables 3, 1, and 2 refer to the Pauli Z, X, and Y, right?
Yeah.
So in the first talk today, Dries showed us that you can, in principle, go to a frame where you can eliminate the single Y term, and then you're going to be left with the standard.
That's exactly.
Does this mean that this geometric effect is due to the change of the reference frame?
That's exactly the case. So, I had this experience of working on circular porous light in Dirac system. I frequently use this unitary transformation to understand that, and I tried that for this example. And I think I have the slide. And you understand this very well. So it's really untwisting the twist. So initially you have this twist, but you can untwist it with a unitary transformation. And by doing this, basically you just make the gap larger or smaller, which is given by this quadratic term kappa. Yeah, thank you very much.
Okay, thanks. Other questions?
Can you explain where is this non-reciprocity coming from?
Okay, so yeah, it's really, okay, so from a mathematical point of view, this value, so when kappa is positive, your gap becomes large. If it's negative, the gap becomes small, and that's it. So in one side, your gap becomes larger, so the tunneling is suppressed. On the other side, it's the opposite, so the gap becomes smaller. You have more tunneling. And probably it's related to the chirality of our system. Yeah.
If you don't include the transition, it remains reciprocal, right?
Sorry?
If you don't include the transition, it doesn't see the same effective and it remains reciprocal.
If I don't
include the transition.
If I don't include the transition.
The interlevel transition. Like the P term is like the how much transition.
Yes.
That's where the non-reciprocity is.
Yes. But we are interested in that tunneling. So we are interested in how tunneling is big here compared to this side.
Okay.
That's the non-reciprocality in this problem.
Yeah. Thank you.
Okay. More questions?
Thanks, Takashi. So you mentioned that for the 3D Dirac driven by circularly polarized light, that at an oblique angle of incidence, you could create Fermi arcs on the surface that should lead to a current one could measure.
Yes.
Which is a nice idea. But my question is, how experimentally could you separate a surface photocurrent from Fermi arcs from some other surface photocurrent that might occur from other states?
Right. As you know very well, distinguishing between Foucault physics against distribution physics or other mechanism, photocurrents, are always very difficult. But maybe one signature is that for this example, which happens at this one photon resonant regime, so the gap size that we have here is proportional to A. A is E over omega. E is the electric field. So this is the current that we generate. And initially, it's kind of quadratic. Okay, so this is against A. And so it's quadratic, but then it turns into linear. So we think, okay, and if I have this kind of band, the current that this band will transport is proportional to this gap, which is again proportional to A. So if experimentally, if you have a crossover from E square to E linear in the large field, that's one signature that it's happening from this. Usually, if you as you know, the photocurrent is a perturbative process, and it's a quadratic in E. But
Okay.
Thank you.
Any more questions? If not, let's thank Takashi again.
Thank you very much.